This is the first video in the completing the model of the atom unit for the conceptual chemistry course. In this video we will be looking at learning goal 1A for the unit. This is the learning goal on the wave model of light. Learning goal 1A says I understand the wave model of light. Our success criteria for this particular learning goal, and we will look at each of these in this lesson. You can see them here, and we will start with success criterion letter A. I can explain the relationship between speed, wavelength, and frequency of an electromagnetic wave. So we'll start with some definitions and examples of some of these terms that we see here in this learning goal. First of all, that term electromagnetic wave. This is just the more scientific or fancy name for the word light. All light is an electromagnetic wave. Now, what a wave is, you've studied in some other science classes, and we've had some brief demonstrations about it in class. So I think we have a pretty good understanding of what that is. Speed. When we talk about speed, it's just how fast the wave moves through space. So how quickly it goes from point A to point B. The wavelength of a wave. This is the distance between any two equivalent points on a wave. So here is a picture of how we might depict a wavelength. So you'll notice here this red line represents our wave, and then these blue arrows with this funny looking symbol, kind of looks like an upside down letter Y. It's actually the Greek letter lambda that is often used to denote wavelength in science. So we have three different ways that we could measure this particular wavelength here. We could go from crest to crest, or the top to top. We could go from trough to trough, or what we call the bottom. Or we could go from one equilibrium point to another. But do notice the one entire cycle, and that's really what the wavelength is, the distance from one point to another after going through an entire cycle, would not be just from here to here, because that would only be half of a cycle, because the wave has to go to its minimum, then to its maximum, then back to where it started to go through an entire cycle. Now notice the length of those arrows are all the same. So the wavelength here, regardless of how we measure it, is the same. Another definition, and you can see it there in the learning goal, is the word frequency. This is the number of oscillations or cycles that a wave goes through per second. So here's another picture that will help us understand the difference between wavelength and frequency. In this top wave here, we have a very short wavelength. You can see it depicted here. Here we're showing the wavelength measuring from one crest or one top to another. And the bottom wave here, we have a much longer wavelength. Okay. Now, the frequency is how many of these waves, how many of these cycles pass a given point in a second. So notice from beginning to end here, both of these waves cover the same distance. So picture these waves moving to the left, say at the same speed, okay, where this entire picture will go, so this end here will go from this point all the way over here in 1 second. So in this wave here on top, I just count here starting from the bottom. So there, that's where it starts. That'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cycles in a second. If this wave went from here to here in 1 second, so that frequency would be 12 hertz. The unit hertz is the unit for frequency. This one, where the wavelength is much longer, notice we would have a frequency of 1, 2, 3, 4 hertz, or 4 cycles per second. So we can see here, the longer the wavelength gets, the lower the frequency. And why that is, and the mathematical relationship for that, we'll see here shortly. So I found a simple GIF, or GIF, however you want to pronounce it, to help us understand the difference between wavelength and frequency and how they're related. So here you can see in this GIF here, on this top wave, we have a much shorter wavelength, or it's a smaller wavelength. Now, an important point here is both of these waves that you see, they are moving through space at the same speed. Okay, you can see if you just start your eye here at the right, as one crest comes, you'll see they just move along at the same speed. So these two waves have the same speed here. But if I count the number of times this little asterisk goes through a complete cycle, I can see here that this frequency is much higher than this one here. In other words, I get more waves in the same amount of time with this shorter wavelength than I do with the longer wavelength. So there is a mathematical relationship that relates these things, speed, wavelength, and frequency for a wave. It is given by this equation. The speed of any wave, again, that's just how fast it's moving through space, is equal to its wavelength times its frequency. Now, in this particular lesson and in this class, we're not just talking about all waves. We're talking about specifically electromagnetic waves or light waves. They all travel at the same speed, which is the speed of light. I'm sure that's a phrase that you have heard of before. Now, the question is, how fast is the speed of light? Well, the speed of light, if you just round it to one significant figure, is 300 million meters per second, or more easily looked at and how we'll use it in calculations because it's easier to work with, 3 times 10 to the 8th meters per second. So that's not meters per hour, not meters per minute. Every single second, light travels at 300 million meters in that 1 second. Just to put that in perspective, that is enough. That's enough distance. If light could travel in a circle, it can't. It goes in a straight line. But if it could travel in a circle, that would go around the Earth 7 times in 1 second. So it's incredibly, incredibly fast. So again, going back to our picture we had before from the couple slides ago, a point we want to make here is this. Because light all has the same speed, okay? Light goes at 300 million meters per second. So picture these two waves here being light waves. Let's say they're moving to our left here. They're both going through space at the same speed. Because of that, no matter what the wavelength is, when I multiply it by its frequency, I always have to get the same number. So this shows us why, if the wavelength increases, the frequency must decrease. Because if one of these numbers gets bigger, in order for them to still equal that same value when we multiply them, the other has to get smaller. Now we can actually be more precise than that. Let's say we were to double our wavelength. Let's say the wavelength were to be twice as long. So let's say this wavelength here, actually this one looks like it's 3 times long. So we'll just go with that. This longer wavelength here is 3 times longer than the shorter wavelength. That means the frequency has to be 3 times less, because my wavelength is 3 times greater, my frequency must be 3 times less. The phrase for this, the term for this, is these two variables are inversely proportional. So whatever factor we change one by, so for example in this case we triple the wavelength, we multiply it by 3, the frequency is divided by 3. Alright, go ahead and pause the video and complete the check for understanding question number 1. Alright, you've had a chance to do that first check for understanding question, and we have completed the examples and discussion of the first success criteria there. So now we'll go to success criterion letter B. I can calculate the wavelength and frequency of an electromagnetic wave. So the next couple slides are just a couple of examples here on how to do this. You'll notice on your note sheet that the problems are already written in there, so you don't need to write the questions. Just follow through the notes and put the solution down as you see this. So the first example, microwaves are used to cook food and transmit information. What is the wavelength of a microwave that has a frequency of 3.44 times 10 to the 9th hertz? So here's the thing. We're asked about the relationship between wavelength and frequency here. We're given the frequency of the light, and yes, a microwave is light, it's just not visible light. We're given its frequency, we're asked to find the wavelength. So that's that equation that we just saw from the last slide. You do not need to memorize this equation, I will always give it to you. Likewise, you don't need to memorize the speed of light, I will always give that to you. What you do need to be able to do though is use the equation. So while I'll give you this equation, just as you see written right here, you need to be able to solve it for what we're looking for and then obviously get the answer. So the fact that we're looking for wavelength here means we want to solve this equation for wavelength. So if I think about my algebra here, if wavelength is being multiplied by frequency, to get the wavelength by itself, I want to divide both sides by frequency. So that would give me the wavelength of the wave equals the speed divided by the frequency. So now that we have an equation for wavelength, we will substitute in our numbers that were given. So the speed, even though we're not given that here, we know what the speed of light is because light always travels at the same speed. And again, I will give you this number. You do not need to memorize it. 3 times 10 to the 8th meters per second. And I divide it by the frequency, which we're given of 3.44 times 10 to the 9th hertz. Okay, remember that unit there, hertz. You can see the symbol there, Hz. That means the unit hertz is one wave or one cycle per second. Now, it might look a little funny here as far as how the units are all going to work and how we'll get the units of our answer, but I'll show you how it all fits together. So if you plug this in your calculator, 3 times 10 to the 8th divided by the 3.44 times 10 to the 9th hertz, you will get 0.0872, and the units here are meters. Now, an important point here is how we end up with that unit. So we're just going to do a little unit check here. In other words, I'm just going to write the units out. I'm not going to worry about the numbers. So we have meters per second divided by hertz. Well, how we get meters out of it, in other words, how the seconds and the hertz disappear is this. The unit hertz can also be written as 1 over seconds or inverse seconds. The reason being is a hertz is a wave or a cycle per second. And it's understood because we're talking about a frequency, we know we're talking about a cycle. So we don't need to write the word cycle there. We can just put 1 over seconds. And notice by doing this, the seconds will cancel. Because this seconds here is in the denominator of the numerator. This seconds here is in the denominator of the denominator, meaning it's actually in the numerator. So they will cancel. And so all we're left with then is meters, which makes sense because we're finding a wavelength. Okay, what is the distance from the crest of one peak to the next peak in that wave? So that checks out. All right, one more example here. Light reflected from a green leaf has a wavelength of 4.9 times 10 to the negative 7th meters. What is the frequency of the light? So like before, we're asked about the relationship between wavelength and frequency. So we're going to use that equation again, speed equals wavelength times frequency. The difference is this time we're asked to find the frequency. We already know the wavelength. So I need to solve this equation here for frequency. So like before, I'm going to divide both sides. So this time instead of dividing by frequency, I will divide both sides by the wavelength. That will get the frequency by itself. And so now we can substitute in our numbers. Again, the speed of the light, 3 times 10 to the 8th meters per second, divided by the wavelength, which we're given of 4.9 times 10 to the negative 7th meters. Again, plugging that into your calculator, you will get 6.1 times 10 to the 14th, and our units here are hertz. Now, again, let's take a look at the units here. Let's do a quick unit check. So we have meters per second divided by meters. Well, the meters cancel because this one's in the numerator, this one's in the denominator. A very common issue or mistake students will make here is they'll cancel the meters, they'll see those will cancel, and then they'll tell me that the units of the answer here are seconds. But here's the thing, if you think about that, that makes absolutely no sense because we're finding a frequency. If you give the unit of the answer in seconds, that would be a unit of time. Okay, and frequency is not the same thing as time. So we want to make sure we recognize here that this seconds is in the denominator because it's meters per second. So our units here, once meters cancel, are 1 over seconds, which recall from the last example we said, that equals hertz. Now if you wanted to write your unit here of your answer as 1 over seconds or inverse seconds, you certainly can, but just writing it as seconds would not be correct. Alright, pause the video and complete the check for understanding question number 2. Alright, so you've had some practice there on calculating the wavelength and frequency of an electromagnetic wave. The last success criteria for this learning goal is to be able to order electromagnetic waves by wavelength and frequency. So the first thing we want to recognize, and we saw a little bit of this in that short video that we watched in class, is that visible light, what we can see, is only an incredibly tiny fraction of the electromagnetic spectrum. When we talk about light, often, just in our layman's terms, we typically just think about what we can see, but a huge majority of light is not visible to the human eye. So this little picture here, or graphic, schematic, whatever you want to call it, does what I think is a good job of showing us the entire electromagnetic spectrum. Now, one thing to note here is none of this is drawn to scale. So while these numbers are certainly correct, you don't need to memorize the numbers. These are giving us the relative wavelengths in meters. So notice radio waves are on the order of 10 to the third meters. It'd be 1,000 meters in a wavelength there. Whereas at the opposite end of the spectrum, gamma rays 10 to the negative 12th meters. That would be 1/1,000,000th of a meter, so it'd be incredibly short. So notice here, working from long wavelengths to short wavelengths, the sorts of electromagnetic waves we have, or at least what we call them, these are all the same thing in that they're all electromagnetic waves, but we just divide them into different categories. We have radio waves are the longest wavelength, then microwaves, then infrared or IR light, then our visible spectrum is kind of right in the middle, then we have ultraviolet or UV, then we have X-rays, and then we have gamma rays. So what you'll need to do is you will need to memorize this order. You don't need to memorize these numbers that go with it. That's not that important to us. You do need to memorize this order. Now, the other thing to point out here is even within visible light, we want to know what order the actual colors come in. So notice this. If we kind of space this out, we can zoom in and pull out the visible light here. There is a predictable order. There is a predictable order that these occur in. Now, you'll notice starting at the infrared end, we have the red end of the spectrum. So notice our visible light fits right here in the middle. Next to the infrared is red light. And then going to the violet end of the spectrum, we have red light, then we have orange light, then we have yellow light, then we have green, then blue, then indigo, which is kind of a bluish purple. I've always maintained that the word indigo or that color was invented just so we could put it in this little mnemonic we have here. And then we have violet light or purple light. So notice when we put those in order like that, these spell out a fictitious name, Roy G. Biv. It's something easy to remember, so you can remember these are just the colors of the rainbow, and we'll make a reference to that in our next learning goal. Why the rainbow, why we see all these colors when we get a rainbow. But if you just remember this name, Roy G. Biv, and the colors and the letters that go along with it, you will then know the order of the colors in the visible spectrum. So for example, if you were asked to tell me which had the longer wavelength between red light and blue light, you should be able to look at this or not look at this. You should know that red is at this end of the spectrum, and you can see this end over here has the longer wavelength. So red light has a longer wavelength than blue light, or yellow has a longer wavelength than indigo light. Likewise, all of these up here, we should know that gamma rays are the shortest wavelength, and infrared is longer than gamma, etc. So what you want to do here, I'll have you pause the video. And then just take a couple minutes, write these down, okay? Write these down, including with the colors, and just take a couple minutes and work on memorizing those. And once you've done that, then go ahead and answer the check for understanding question number 3 there on your note sheet. Alright, so you've had a couple of minutes to work on memorizing that and doing the check for understanding. You're not going to have these memorized in one sitting, most likely. Just work on this a little bit every day for the next few days, and after 2 or 3 days, you'll have this order down. You will know what this order is, starting with the longest wavelength, going to the shortest wavelength. Alright, so that was the last slide here for this learning goal in this lesson. So we now have an understanding of the wave model of light. So we'll be working on this. The next video in the next lesson will be on what we call the particle model of light. And we'll look at why we need 2 different models, why we need a wave model, why we need a particle model.